Well, I came a long way for this talk today, so it's great to be here. So I'm going to tell you about things that I hope will connect with some of the interests of people in the APS and elsewhere at Argonne, starting out with some polymer nanostructures, and both at the molecular level and nanostructure formation, and how you control them. But then I thought if I just had to talk about scattering for this audience, and we have a 1 angstrom source in my lab, but it's not X-rays, it's low energy supersonic beams of helium atoms, which I'll tell you about. And then about half my talk today will be on energetic embedding in ice, which we just published our first paper just a couple of years ago. But it's rapidly taking over several parts of my group, and it touches with energy science in many ways, notably clathrates and things, so we'll see how that goes. So I'm very glad to be here, and thank you very much to my kind hosts for the invitation. Now, when I travel to places, frequently people think I have very large laboratories for a chemist or a physical chemist, but seeing several of you took me around the ring today to show me your beamlines, and it puts me in my place. But we have in my group several instruments for studying gas surface interactions that you'll get to learn about in the next hour, and also scanning, tunneling, and atomic force microscopes for local visualization of processes, and support the usual TEM and SEM. But I haven't taken the plunge into the beamlines of Argonne yet, but I had a chat this afternoon that may change that, so we'll see how that goes. So I'd like to start with just some comments on polymer nanostructures. Polymers are very nice because you can control their architecture, you can control their phase diagram, they're very useful for materials of all sorts, and we'll help talk about using them to understand their dynamics in the next few minutes, and also on different length scales, both initially on nano, but then very much with scattering at the molecular level, as you'll see. And one of the ideas is to use self-organization of polymers, and we had a paper just a few months ago on organizing nanorods to make very efficacious enhanced Raman spectroscopy substrates for trace gas detection. So it leads you into all sorts of interesting directions. I think you all understand the paradigm for self-assembly, but the idea is you snap your fingers and you don't have to do lithography that takes a long time. And in fact, there are now electronic devices, dense memory devices being based on self-assembly, not lithography fully. So it's a very interesting time. This is the one slide that I'm showing for one of the old group members from my group in the audience, but basically diblock polymers are where you have a hydrophilic group, a hydrophobic group. They're put together, they don't like each other, and they can phase separate if you heat something above the glass transition. When that happens, different structures form spontaneously if they have the right physical properties. And in particular, in the bulk, you can make spherical phases, cylinders, lamella sheets. And on surfaces, it gets very rich. And I was captured by this several years ago. And in particular, you can pour polymers onto a surface, and it looks like a fingerprint. You'd all agree that looks like a fingerprint. That means there's no preferred direction. It's confused. So when it phase separates, there's no difference between left and right and forward and back. So they're not highly structured other than they phase separate. You also can tune the chemistry, and they can lie down flat or they can stand up. Now, something we got into a few years ago was refining graphoepitaxy, which is a fancy word for saying you pour the polymers into nano-confining channels. You control the chemistry along the edges of the channels, and you can guide structure formation. And we've gotten very, very good at this, and we use it for all sorts of fundamental tests of polymer physics that I'll tell you about today. Just to show you, if you pour polymers into a channel, it looks very disconcerting, but if you look at the edges, you'll see that actually the boundary conditions, if you have the right chemistry to do the right wetting, lines up beautifully. And then if you heat it up above the glass transition, you can end up getting structures that are remarkable. They have lines that are maybe 15 nanometers wide. They can extend for tens of microns, so they have tremendous aspect ratios. And that can be the basis for nanofluidics, electronic devices, sensors, biological platforms for where you want to have structures line up. They're very useful. What I'm going to tell you about is only a year or so old now. It's going to be a very new talk, I hope, for all of you, so not much old stuff at all. You've all heard about the single molecule revolution. I mean, the Nobel Prize last year in chemistry was for visualizing that with super resolution spectroscopy. Well, another way to look at structures is with a microscopy based on STM or AFM or electron microscopies or X-rays. And we're going to talk about looking at defects. These were published just about a year and a half ago. If you remember the fingerprint picture I showed you as introduction a few minutes ago, it's full of defects, disclinations, dislocations, and there's been a generation of beautiful material science and physical chemistry where you look at synchrotrons, you look in the bulk, and you see on the average how things evolve with annealing. So you get out a lot of average quantities. It occurred to me maybe 3 years ago, what you really would love to do is to get rid of that and look at single events. And so we've been striving for that. So this is one of these almost perfected stripes that I bragged about a moment ago. But if you really look closely, I challenged this spectacular student, Chen Tang, one of my best ever. Could you find a region that had only 2 defects, so not 50 defects and not none? And she said, of course. And so she looked around, and up here there's a defect, and here there's a defect. We heated above the glass transition temperature. It turns out the stress fields for these are attractive. It's like a tractor beam, and so they want to approach each other. And you can watch this for, in this case, over half an hour. And you can find out that as they approach each other, if they have the right mathematical properties when they get there, they annihilate. So this is not averaging dynamics over 10 to the 23rd, of these kind of structures. It's looking at only 1. And it's very powerful to do that. You can look at the attraction due to these forces are well understood, but basically it predicts that the distance should converge as time to the 1/2 power. And this is something we wanted to test. And for disclinations, it's time to the 1/4 power, which I won't go into today for time, but we also tested in this series of papers. And these are the beautiful data that made me, smile with a great student. It's one of the joys. And it shows as a t to the 1/2 power convergence of 2 defects over different length scales. And from that, this is going along the direction of the channel. And you find a diffusion coefficient of about 10 to the minus 12. And that's not inconsistent with what you might get from theory. And these are some of the first measurements of single defect approaching each other in polymers with this precision. And you can measure this many times, and you can get good statistics. Moreover, you can ask, well, how far can this work? Clearly, this is being done at high temperature because you're above the glass transition. And so you have to have enough thermal energy in your system for the defects to attract each other, right? If they're frozen, so you have to be hot. And once you're hot, you can ask, what's the thermal energy in the system? Because when the attractive force is equal or less than the force due to the thermal fluctuations, nothing happens. They wander away and get lost in the forest. And so that turns out to be about 4 microns. So there's plenty of distance over which you can study these kind of phenomena. Now, I described one kind of motion, which is called climb just now. Another one is defects that are moving crosswise and then annihilating. This is called glide. And this is different because remember I said each of the polymer chains has a hydrophobic side and a hydrophilic side. In the prior one, they never have to go into the unhappy domain. To go this way, they go crosswise. So the hydrophilic domain has to scooch through the hydrophobic domain repeatedly when you do this. So it should be a higher activation energy. It should be much slower. And we've measured lots of these. It, again, is t to the 1/2. But the mobility is much less. And it's about an order of magnitude. And so we're able to see the anisotropy in motion of single defects very clearly. And at different temperatures, you can run the kinetics if you're a chemist or materials type person. And you can learn an immense amount about how polymers percolate, which is what we did. You can get out the activation energies for these processes, and they're order of 180 versus 240 kilojoules per mole in those two directions. And so, again, you can extract in a mean field a lot of this from X-ray scattering on a bulk, but we're looking at them, effectively single defect at a time. And you can learn a lot about the details and how the local environment affects those details. So it's highly complementary. And I suspect with your great upgrade that I hear a lot about it somewhere, that you'll be able to image in and do things like this with X-rays in the future very nicely. So that's sort of an introduction to some aspects of this. But the story from there expands quickly. This is a movie I'm going to show you where the domains in these confinement channels are color-coded, with green being along the direction of the channel, and the rest are color-barred here. And you can see how domains Pac-Man each other up. So all these things, if you have the right chemistry decorating the edges, want to line up along the channel. And what you can see here, don't blink, is you can make time-resolved STM movies where you can watch all the domains turning. I call it being Pac-Man or Pac-Woman, I guess, so that they all end up being in this perfect alignment. So you're seeing now the ability with time-resolved atomic force microscopy to monitor not just single defects moving, but to actually watch whole domains being consumed by lower energy states until everything reaches the ground state. And so there's a whole hierarchy of understanding that's being developed now about how you do this. Now, when you put polymers into wedges, that is, channels that are not straight, you'd love to do that to make some devices, I'll suggest to you, but also to understand other aspects of polymer dynamics. Some of you work here with metals or semiconductors. They're phenomenally unforgiving. That is, if you have the wrong kind of epitaxy or something, you grow amorphous or highly defected materials. Polymers, like rubber bands, are very nice. You can stretch them and push them, and they'll tolerate, 10% distortion before they do bad things. And so in a channel, there's a certain number of periods, each of which is, let's say, 20 nanometers, that is a magic number when the width of the channel is exactly equal to a multiple of that. And when you're at the half point, it's very confused. It'll either make a dislocation or consume a dislocation. And so you can do some very clear theory where you can predict what happens when the polymers are expanded or compressed. And you can predict that you will break into certain positions. These are a series of defects that we've imaged in just this one image where you can see the magic numbers are showing up. And in particular, you can now do some theory to understand the confining potential that leads the polymer domains to be compressed or stretched or perfect. And what happens is in narrower channels, the propensity to form the magic number is much stronger due to the sharpness of the potential than in very wide channels. So there's a limit to how far out you can go, and these are the potentials you can calculate versus number of domains you plot. So it's much more enforcing at smaller sizes. What this means is if you do, again, time-resolved imaging, this is 2 hours of the same spot at high temperature in a controlled environment, no oxygen so it doesn't cook, you actually can watch the defects migrating to their magic number sites, and so you can see the effect of stress fields on the mobility. So this is now not free mobility, but mobility with different stress fields applied depending upon the angle of the wedge, and you can learn an immense about there. And again, these are single defect mobility studies, so it's not averaged, right? That's the whole point. You can watch how they go with distance and do the kinetics. And it's a way, if you care, to place molecules and nanoparticles at certain distances that are self-organizing because the defects are binding sites for many types of nanoparticles or molecules if you do the chemistry right. So there's some interest in using them for those kind of purposes. Now, what I'm going to show you now was a dream for me a few years ago. And if you take some of those channels that I've mentioned to you in the last few minutes and you have them intersect, you can ask what happens in the intersection region with the domains. Some of you may want to make microfluidic devices or nanofluidic devices or electronic devices. You can make conductors and insulating domains. And it turns out that they're degenerate. So here's an intersection where you see this going this way, and here's one where they're going the other way, right? You can see that, I'm sure, in the back, I hope. And here's one with a 4-4, we call it, where there's 4 domains coming down the highway. And this one goes upper left to lower right. This goes lower left to upper right. So they're degenerate. You never know what's going to happen because energetically it's the same outcome. You can make massive parallel grids of these. And if you use those at least in the front, if not in the back, you can see some go this way and some that way. And so if you want to make switches and devices, you wonder, how should you do that? And the answer is you can put on electrodes to steer them, in principle. They have different dielectric constants, the 2 domains, and therefore you can put an alignment field on them. And if you do that, we've built devices to try to do that. It turns out that you get the ability with prior to the field, it's confused. This is one of these domains where if you average enough of them, there's half going one way and half going the other way because they're equal. But once you turn on the electric field, which is up here going this way, all of the domains line up. And it means that the intersections you can predict with certainty of how the connectivity diagram of all those nanostructures work, and it's self-assembled. It's really cool. And Paul Neely and Wanda Pablo said, Steve, it's frustrated. You'll never be able to turn this into that. And then I showed it to that, and at least one said, yeah, it should really happen. That's great. So it was really a very interesting discussion. Don't tell Juan or Paul I said that. OK. So, and we're going to be using this for some interesting switches of these sorts. The last application on the nanoscale just was a few months ago, where we decided to see how nanoparticles can be structured in these polymer structures that we make. So it's a hierarchical assembly question. And here, when you make a polymer that's a die block with the right properties, you have these stripes that could be on the top. You can either burn one out with light, which is an old method that works, or you can swell it with different chemicals, and you can change the topology of the polymer just with liquid chemistry, which, yes, Seth, I've learned to like now. I never would have done this a few years ago this way. But basically, the initial corrugation might be less than a nanometer, well below a nanometer of the polymers. But after you swell it with liquid acetic acid, you can get corrugations that are maybe 6 nanometers. So you're going from something that's almost smooth to a corrugated channeled structure that's self-organized. You now can pour your nanoparticles on top of that and see, can they themselves self-organize? And what we decided to use were rods. These were made by Philippe Guillaume-Sionet's group and his great student Ed. And when we do this, we can make different aspect ratio rods. So in the paper, we talk about all of these kind of details. But it turns out the idea was to use wetting phenomena that would drag rods into these channels and see if it worked. So we decided the way to prove this before we actually looked with microscopy was to do optical measurements using surface-enhanced Raman spectroscopy, tuning into the plasma of an array of rods. And if the rods were all lining up as expected, there should be a great anisotropy in pumping the light field along the rods versus perpendicular to them. And what we find here is with benzene thiol sprinkled on top of these channels that have the nanorods, there's a complete anisotropy between exciting with the polarization along or crosswise. So that suggests that it's successful. What we really did to prove the point is we then did AFM on these structures. You can see the rods lining up in the channels, more or less, not perfect. But what's very interesting is you want to make sure that you're not getting false signals from the areas that are not within the confining channel. So we actually did some microspots where we scanned a Raman laser system across the channel, and you can see the Raman enhancement at different vibrational modes of the molecules show up just in the channel. So we showed that we had high efficacy for this. It has very good detection. It has a very strong Raman signal. And the Department of Defense is considering detecting trace gases with structures made this way. So that's interesting. And this was all done recently. Now, this is what's coming in the future. I've talked about time resolution, but what we've done until this slide was what I would call and you would call time lapse. You know, if we took an image and every image took a minute to take, but if the phenomena takes an hour, it's great. You still can make a movie. But you know, things are getting better, and we now have a almost video rate AFM working as of 2 months ago. And this AFM has made the ability to watch in essentially real time. Oh, come on. Oh, phooey. So this movie's not going to work, but you were about to see a real-time movie of how these domains moved. Maybe at the end I can pull up a different file, but I won't stop right now. But the ability to take, you know, images in a second or less means that you can watch completely the domain evolution, not once a minute, but basically on a time scale fast compared to how they move, and therefore you can visualize great details about the mobility. And we are proposing to use this in some water experiments done maybe with argon someday, if we're lucky, where we would make these materials and we could flow water through them and purify water. And a lot of that we'll be able to look at these kind of structural changes in real time, in liquid, to see how this goes. So I think that's very exciting. So for those of you who would like to leave the nanostructure world and go down to the molecular world, we've arrived. And now I can talk about scattering, so a lot of you can perk up in your seats and intro too. I see a few of you doing that already. But we decided in our group, and I'll tell you about this, we deal with hard scattering probes that are about a de Broglie wavelength of an angstrom, but they're not X-rays, they're atoms. It turns out helium atoms at low energy can have even sub-angstrom wavelengths, and because of that, you can do scattering, structural scattering, but we also do inelastic scattering, and actually some coherent scattering. There's all sorts of things one can do. And I'm going to show you one of the first studies ever done of looking at polymer dynamics with atom scattering done in PNAS about 2 years ago. And we're going to ask why we want to do this is that, by the way, the atoms are only surface sensitive. There's no penetration at all. So it's like skipping a rock on water. And in fact, here's a rock skipping on water. And that's the way atoms can be viewed. They don't go in whatsoever. So that's you know, a difference from neutrons and X-rays. Just to show you and get you calibrated, I suspect everyone here knows about self-assembled monolayers of some level. I will tell you this, the people that come out of, and some of you may out of the famous school from Harvard, George Whitesides, is very different than the descendants from Jacinta Scolas or others. Some try to grow crystals that are perfect, and some put SAMs onto a surface, and the quality can be very different. We can diffract from these SAMs with atoms and get beautiful diffraction patterns. And we can look at these with atomic force, or STM rather, and you can see the patterns formed that are very beautiful. And so you can look in real space or reciprocal space. Now, when you do a diffraction pattern on these polymers, you can see this very beautifully. And when you look between diffraction patterns, this is on a crystalline surface, not yet amorphous, it looks like there's no signal there. But as all of you know who do your kind of beautiful work here at the APS, that if you blow that up times about 100,000, there's beautiful signals buried in that very little background, which are the K-resolved energy spectra of the system. So it's the phonon spectra, much in what you could do with inelastic neutron scattering or X-ray scattering, except it's surface sensitive. And we now will use that to look at some, just for today, a few minutes of polymer structure on a surface. So we have PMMA, PS, polystyrene, polybutadiene. These are the regular test molecules for someone in this kind of area. And we decided to take a look at systems which can be amorphous or crystalline or have grain boundaries to see what we could learn about the polymer system. The system we're going to deal with is PET, which is polyethylene terephthalate. And in this system, there's a bond per unit, which can be gauche or trans with respect to the oxygens. And this one can lead to crystallinity, they pack, and the other one could be amorphous. And we're going to ask, how can you probe that? Well, this has been known well before we joined in the field. You can take infrared spectra, and there are certain vibrational modes of the polymer which are indicative of cis, gauche, or trans conformation. And so we built an instrument with a Fourier transform spectrometer to support our helium scattering lab. This is Hongshu Yuan. She now works somewhere in the bowels of Silicon Valley. And it turns out that we could beautifully see the key modes, which are telltales for the trans, meaning crystalline, or gauche. And so we can do this. We can grab spectra in time, so we can watch kinetics of annealing. And so we're able to watch an amorphous film turn into a semi-crystalline crystal. And why this is important is that we didn't want to fly blind in our scattering lab. So we can take samples with a procedure, make sure it works every time or almost every time, and then move it into our atom scattering lab and have some assurance that it works. So this began with a very brave woman, Miriam Friedman, who said, I want to do polymers, Steve. She didn't want to do all these crystalline materials. And as all of you know, I suspect dealing with amorphous systems is much, much harder than crystalline. And in particular, if you take polymer chains and you put them on a surface, they can pancake, named after de Gennes, the de Gennes pancakes. And you'd like to understand what are the dynamics in Miriam's state, which is just going to be a slide or two, of a thin film of polymer. And the question there is a classic one in materials science, which is when you have something and you make it confined smaller and smaller and smaller, when does it know it's confined? That is, when do the properties deviate from the bulk? And that's a lot of people at synchrotrons here, maybe some of you do this by looking at supported or unsupported films. And this is, 5 years of Miriam's thesis in one slide, but basically we were able, after an immense amount of work, to see signal levels coming from the amorphous system. There's an early publication on that. We looked then at multiphonon scattering, and we do this versus temperature. So it's sort of what you would call a Debye-Waller type signature. And we could ask, how do the fluctuations at the change of the surface of a polymer versus thickness and temperature of the film? And we did that. And we found out, very interesting thing, is that at about 50 nanometers or so, the mean square displacements perpendicular to the surface were those of the bulk. But when we got down to distances of order 10 nanometers, they changed by about 15%, and they got stiffer. This is change per degree Kelvin. And so we're able to really see the differences of nano confinement of a polymer where the chains know there's an upper surface and a bottom surface. So that's a very clear signature. A bit of history. I won't show too many math slides today, just a couple. There was a question, how can you use atom scattering to look at a polymer? I mean, it was developed to look at crystalline metals and semiconductors. And it turns out that you can write down the differential cross-section for scattering based on hitting discrete centers or hitting something more like a trampoline. And without all the details, one of them has a t to the inverse half, and one has a t to the inverse 3/2 dependence. And Miriam was able to look at this, and we could understand the data looked like one and not the other. And so we now knew how to analyze the data. That's the point. So we learned how to do the scattering theory and dynamics, and then that taught us how to use it to do materials physics. So this is one of our beamlines. This is the next generation with Ryan Brown and Jim Becker. It's a time-of-flight machine. It's something that you would all recognize, at least the ones of you here that go into the labs, meaning the synchrotron. It has a 2-ton detector. It rotates around and around. And we can do K-resolve scattering with high precision. We have wave vectors of 4 to 11 reciprocal angstroms. You can do the scattering, and you can find out the Debye-Waller factor for the scattering can be decomposed into a perpendicular and parallel component. That's very important because you can look at chains jiggling perpendicular to the surface or parallel to the surface, and you'd like to know how do the dynamics work for that. It's also a bootstrap mechanism because if you go to a specular condition, there all you see are perpendicular displacements. You have to go off specular to see scattering that's picking up a parallel component. So if you could do the one component and get a really good answer, and you do it off scatter, you can get both. So we do that just to show you that we have to fight for signal like you do. We can take data with either choppers in time that are single shot, conventional, or we also have pseudo-random choppers, cross-correlation choppers, if you will, so we can get a duty cycle of about 50% with high time resolution. This was invented in the 50s for nuclear physics experiments. And we can convert that to a time and then to an energy transfer spectrum. So we were able to get out these kind of decay curves for the Debye-Waller signatures, and we were able to extract the mean square displacements perpendicular to the surface of the polymer. The data look very pretty, and from this you can get out how the displacements versus temperature change. What's the gradient perpendicular to the surface, 10 to the minus 4. Then doing what I just said, you can do the bootstrap, because if we know this number and we measure this number off specular, we have access very directly to displacements parallel. So we're learning how polymer chains are wiggling and jiggling. We do that, we see nice signal levels, and with that we can extract out mean square displacements parallel to the surface, which actually are a little bit 10 to the minus 3 in this direction. You can do this for the amorphous versus the crystalline polymer, and you can find out that the crystalline PET is slightly softer than the amorphous material. It might be counterintuitive, but there are several examples in metallurgy where things that have big grain boundary content will do this, and this happens in the polymer systems as well. And you can look at the scattering off specular, on specular for the crystalline, and therefore you can extract out how this changes for both the perpendicular and parallel. So we have a very good understanding that can be compared to theory of how chain displacements versus temperature go using this method. I want to show you the sensitivity of the method in case you'd like to appreciate that. So if you have a mean square displacement that you vary from 3.1 to 3.5 or 2.5, and these are the data, you can see that there's a tremendous sensitivity to the displacement field for the polymer chain. So it's a very sensitive method for probing polymer dynamics. You can check it, as my student liked to say, but basically this is putting the answer back in and recalculating what you'd see, and it all works very well together. So in summary, we're able to look at mean square displacements for polymer chains, crystalline amorphous, and we can see differences. We can compare this to neutron scattering and helium scattering on self-assembled monolayers, and it's very interesting for those of you who work with soft materials to learn how polymer chains sort of flop around in the plane where the polymers are confined versus jostling up and down, and it's a very good thing to learn about. Okay. I'm now going to take you to something we're just doing now. So, this is current, so you haven't read much about this except for the first 2 papers, perhaps. And this ties into some aspects of energy before I move on to the ICEs. It turns out that you all know about hydrogen-decorated silicon. It makes the world go round. Silicon Valley, the whole world works on that. If you want to move a silicon surface into air with hydrogen on it, it begins to decay immediately. It doesn't fall apart in a second, but it's highly reactive to room temperature and oxygen. If you want to make fuel cells or certain types of electrochemical cells, maybe batteries, it turns out that methylated silicon, methylated germanium, have much better redox properties than does regular hydrogen silicon, hydrogen germanium. Nate Lewis's group at Caltech in their Energy Hub has been working on this for several years, and we've partnered with his group to get those materials to Chicago, and we've helped him refine the synthesis of those materials, and now they make very highly perfected films. They weren't originally, although they were very good. And the instrument we use is the same one we started with the polymers, but we now have the ability to go into a more sensitive mode, which is what we use for the polymers. But now we can move the detector out. It's all on optical rails. It takes a day to switch so that we can do high resolution scattering in both time and K. And what we will tell you about just for a moment is you can see gorgeous diffraction patterns from these materials, inelastic scattering, and we do electronic structure with partners and molecular dynamics simulations. So we're learning all about the material. For the chemists, the real chemists in the audience, it's a synthesis which to me looks simple, but I'm sure not many groups in the world do it. It's a Grignard type reaction on the semiconductor surface, and you can make methylated silicon or you can make methylated germanium. And if you want to do this tonight in your kitchen, please read some papers from Nate Lewis's group and not from my group. Okay. Why you'd like to do this, again, is you protect against oxidation, structuring of the surface, and it also provides insolubility in water so that you have a stable interface. This is just a summary of a gorgeous thesis by Ryan Brown and a newer one by Zach Hun next month. But basically, you can do all the reciprocal space kind of work that you do so expertly here with X-rays. We do it with helium atoms. You get gorgeous diffraction patterns along different symmetry directions, so you learn about structure. You can look at the intensities to learn about charge density profiles of the surface. But very importantly, you can do inelastic scattering, right? This is really the reason. So we can look at phonon structure of the material at the interface across K-space and learn about the interactions. And you can do theory to see how well you're doing. So we did all of this. And we got out some very nice spectra for methyl silicon and per-deutero methyl silicon. We have theory work, DFT from Europe, and then we do molecular dynamics simulations in Germany, and we're able to get these kind of results. And many of you may know, maybe not, that there's something called a Rayleigh wave, which is the main propagating surface wave, Lord Rayleigh, that happens on oceans, but it happens at the atomic level. It's a mode that lives at the surface. It decays exponentially into the bulk. So it's not a projection of a bulk to the surface. It's unique to the surface. And you can look at those modes. And what was very interesting is that the answers we saw experimentally and not initially theoretically. By the way, the experiments preceded the theory, so you've got to keep them honest in that way. And we found out that there was some very strange happenings in these surface waves. Polarizations were switching, and positions of modes were moving. And it turns out if you take a look at the symmetries of the methyl moving, the rocking, hindering, and moving, and couple them to the Rayleigh wave, there are some places in reciprocal space where there's a resonance. And it only happens in a specific place in K-space, which is where we saw it. So the theory was done. And because of that, we were able to understand one of the first aspects of how you couple modes that exist due to overlayers that are organic with the semiconductor across K-space. So it's a full mapping. So it was very interesting. We also can now switch to methyl germanium, which will be for higher speed transport type materials. And the synthesis ain't so good as we say in Brooklyn. If you look at the wings of the germanium, it actually has substantial more defects than the silicon. It still diffracts beautifully. I mean, these are diffraction patterns of methyl germanium and methyl silicon. The spacing of the lattice is different. But when you look at the line shapes, you can do in and out of phase Bragg scattering. You're one of the only audiences where I don't have to explain that, I suspect. And so you can really parse step structures and point defects and things of this sort. Finally, the last frontier for this work for us is to look at the librations and the rotations of the methyl groups. Are they free rotors? Are they hindered rotors where they librate? Where they locked in place? It turns out the silicon theoretically has a very high potential because it's a smaller lattice. But germanium, depending upon the level of calculation you do, drops down to, it's still larger than thermal at room temperature, but the Boltzmann tail can access that. And so I think it's going to be very interesting to look at locking and unlocking of the methyl groups on germanium. We have partners in Germany again that are calculating this, Giorgio Benedict and coworkers. And what they've done so far are just some potentials where you take different geometries for neighbors. But what we really want to do is a full MD, and this is now going on currently, so this is just happening now, where we're going to really look at how the whole system, when you allow everything to move and jiggle and rotate, gives you these barriers. And we have our first low temperature STM results where one can now look at whether these things are rotating, which gives you a halo, an annulus in an STM image, or whether they're locked and give you a threefold dot pattern, right, if you really look with an STM. And so we now have a helium-cooled STM in my group that works, and so we're going to do that. Okay, so for those of you who came to hear about ices and clathrates and things, this is the last part of the talk. This is a different type of scattering that you'll appreciate again. And it turns out that, I don't know how many of this happened to all of you, but we did an experiment that we really liked, and we published it in a physical chemistry or chemical physics journal. And then, you know, I and my students and postdocs started getting invited to go to astrophysics meetings. It's very unexpected. It turns out that there's an immense interest in molecule interactions with ice on dust grains in space, molecule formation, comets, chemistry, moons of Saturn, all sorts of things. So I've learned a lot about astrochemistry. This just started a couple of years ago and it's ongoing. This is on the pretty poster that Argonne made, for which I'm grateful, but this is a graphic where we're talking about how molecules embed into ice. So we discovered a new mechanism by which atoms and molecules go into ice about in the last 2 years. And we got a press release from the AIP, and it was fun. It was a news bubble for 15 minutes, but it was nice to have the 15 minutes. And the first work on this was featured in a special issue of JCP a few months ago. So what's the story? If you have, and we'll start for the first 10 minutes with atoms, then we'll do molecules and clathrates, and we'll call it a day. So when you have an atom that strikes a surface, several things can happen. You can scatter, which we've talked a lot about already. You can stick on the surface, and once you're on the surface, you can ooze into the bulk, maybe, if it wiggles in. You can sputter. If it's a high enough energy, incident atom can sputter off surface particles. And the new channel is embedding, where actually maybe you can go directly in. This is done in a different instrument initially, and then it's in our infrared lab now, where we can scatter. There are two machines we use to do this experiment. And again, I consider them large for a physical chemist, but again, it's hard to compare with what you have here. But this is a quadruply differentially pumped molecular beam that strikes a surface. We have a mass spec that rotates. This is very good for looking for scattering. It's probably one of the best machines in the world for looking at scattering of molecules. The other one is where we have now a very bright infrared spectrometer beam looking at a surface, in situ, in real time as we scatter. So one of them can look at things that have optical activity, and one can look at reflection. And so we started with ice. Everyone has to start with ice when you look at condensed films. And we were able to grow ice over 200 layers, and you see a spectrum of ice in the infrared growing in. We figure out the absorption depth, so you know how thick you can go before you don't have sensitivity to the film anymore, and off you go. So the first thing about ice, you can, as I said, scatter from it, and if you scatter from it, you can have different occurrences. You can either reflect from the surface directly, that's called direct scattering, or you can absorb on the surface transiently, walk around, and then re-evaporate, and that would look like a thermal distribution when you scatter. We see all of that. The other phenomena, if you're using high enough energy beams, is you can sputter molecules from a surface. These are from some of our first work on ices, where we were asking questions about sputtering, where versus the beam energy of xenon into ice, we can actually watch the amount of ice go away. So we were sputtering it off, and we can look at infrared spectra of the ice, or we could do thermal desorption, and you can learn a lot about the kinetics of that process. What I find very interesting is you can look at the energy dependence of sputtering, and for those of you who started out in the gas phase, I know some of you do combustion work somewhere in the audience today, you can ask, compared to the sublimation energy of ice, is there a threshold? And it's not perfect, and we could do this with isotope dependencies. And basically, we have a good understanding of sputtering. We also have molecular dynamics simulations that follow the experiments. So it's understood. Now, ice. So ice comes in many flavors. No jokes about Ice 9. But the two that we'll talk about today are crystalline ice and amorphous ice. You can differentiate them both by their thermal desorption spectra as well as their infrared spectra. One of the great DOE labs besides yours is PNNL, and Bruce Kay is a dear friend of mine, and he has pioneered a lot of work on amorphous versus crystalline ice, so we talk about these experiments together. You can take a look at the spectra, and one thing we'd like to know before we go too far is if you grow an amorphous ice and you're hitting it with energetic particles, do you cause it to be crystallized? Can you do a crystallization from the energy of the beam? And it turns out for ice, meaning water ice, the answer is no. It's locked up enough with frustration that it won't do that. Moreover, you can do thermal desorption, thermal programmed desorption, and you can see that there's a different shape around 160 Kelvin for amorphous solid water desorbing versus crystalline ice desorbing, and that's due to a phase transition that occurs just below 160 Kelvin. And we can look at it both ways. Can you take crystalline ice and make it amorphous, or amorphous make it crystalline? And ice doesn't change with bombardment, at least in the thickness of the films that we're studying. It's not a monolayer. Okay, so now this is where it all changed. We did an experiment with this sputtering, and we noticed that we had xenon at high energies coming off when we do thermal desorption. When we do low energy xenon hitting the surface, that peak is absent. So it's, So it's absent here, and here you see this present thing. I should tell you, this is being done at about, 115 Kelvin. Xenon does not stick on the surface of ice at 115 Kelvin. You have to go down to about 60 Kelvin for that to happen. And yet we're seeing xenon emerging from the system, and after you think about it, it suggests that, wow, maybe the xenon is going directly into the ice and becoming intercalated or frozen out inside. And so we've studied that versus energy of the beam systematically at different angles of the beam, and sure enough, you can see with increasing perpendicular component of the kinetic energy that the xenon peak grows in. So you're embedding atoms into the ice versus increasing kinetic energy. And you can do this for both amorphous solid water and crystalline ice with higher probabilities, as you'll see in the amorphous ice. So one of them seems to be more stable. If you look here, the xenon in amorphous water stays to 150 Kelvin before it blows out, whereas the one in crystalline ice is about 140 Kelvin. And this is because the disorder intrinsic to the amorphous solid water allows it to reform a nice pocket to hold the xenon to higher temperature. The crystalline state is less forgiving. We, of course, wanted to do more than xenon, and so we tried krypton, different momenta versus energy characteristics in the collision is smaller. And we find out that you can embed krypton also. You can look again at comparison of the xenon and the krypton, and we find out the xenon embeds deeper. It's 10 times more probable, but there's a loading factor. We did these experiments, and we found we couldn't just keep doing the experiment. It actually, you'll see in a moment, saturates, so it gets very interesting. So the question that I think follows is, where does the gas go once it's inside? Does it like a parking space in a parking structure? It goes and it's stuck. Or is it percolating around, and is it dissolving further into the ice? And so we will find out that, in fact, when we grew embedded krypton in ice and then intentionally grew 1, 2, 3, 4, 5 layers of ice on top of that ice, we could then do a desorption experiment. If I'm not going too fast, I apologize, where you can see whether or not the gas comes out. And that tells you a little bit about how thick the film is, where the krypton can communicate with the surface and the air. And it turns out that, in fact, it's depressed. It doesn't even happen, basically. So we find that 4 or 5 layers of ice is enough to stop the krypton from coming out. So that tells us very directly the entrapped rare gas is in the first few layers, because when we heat it without the capping layer, it does come out and desorb. So what we have also are saturation or suggested saturation curves for the rare gases, where it looks like it's filling up. There's an initial slope for probability of embedding versus dose, but then after more time, it seems to suggest saturation. And in fact, that's seen very clearly in the data. The data are really very clear. The same thing happens with xenon, where it seems to be saturating versus time. And so for this, we turn to someone who many of you may know, Bill Haas's group at Texas Tech. He's a long-term many-project collaborator of mine and continues presently, where he does very realistic molecular dynamics simulations that can model. He really prides himself on being able to model the experiment as closely as possible. He does angle resolved, energy resolved, so he can really match what we do experimentally very well. And he shot xenon into ice, and he found out that, in fact, what I suggested is correct, that it goes down either between layers 1 and 2, 2 and 3, or 3 and 4, and then it shuts down. It doesn't, enough energy is dissipated as the atom goes in that it doesn't go all the way down. And so these data we published jointly suggest all of what I told you. A very interesting thing, which was in a subsequent work, is that he also showed that when you go in, under many conditions, it also comes back out, which we see experimentally. So once you're in, you shouldn't think that the lattice has locked you in forever. It's some of the trajectories, a majority of the trajectories may in fact percolate back out. And they can be differentiated from the ones that directly scatter, again, by the angular distribution and by the energy distribution. So you can parse that. Okay, so on to molecules. This is the last little bit for the talk. We certainly wanted to move into molecules embedding in ice. As you know, once we knew that the astronomers cared about this, it became very interesting, because when you have 1 billion years on very cold ice grains, you can accumulate a lot of molecules if they stick. And sticking is relative, because a lot of the particles are fast. But if you have a way of embedding into ice, they can get trapped, and then you can do chemistry, and maybe you can make life. All these important things start happening. So we studied CF4, which has a whoppingly strong infrared transition, and we found out that in amorphous water, indeed, it can embed in much the same way that I talked about for xenon and krypton, whereas for crystalline ice, it's basically at our detection level. And so this is telling you that the probability, at least at 6 volts of kinetic energy, that we have the ability for these larger molecules to embed into amorphous water ice, but not into crystalline ice. And we've studied this in detail, published in a different feature article in JCP a few months ago, where you can follow with the strong absorption spectra the probability of it going in, how much goes in. You can get out the kinetic processes versus kinetic energy. And so we've learned a great deal about a model system, CF4. Now, this is all leading up to the Department of Energy, so you're also supposed to sit up another inch taller now. There's real worries with global warming about the permafrost going away. There's real interest in clathrates that are under the sea, either being mined for methane or the clathrates dissolving, right? And there are eruptions that have happened around the world recently where massive releases of methane have happened spontaneously. So people are worried about that. And so we have now in the process of writing our first paper on CO2 interacting with ice. And what we're very excited about, after we add a lower temperature manipulator this summer, we're going to look at methane to really begin to have access to methane clathrates, but maybe not at high pressure. So that'll be very interesting. Clathrates. They are localized all over the world. There are known deposits that are shown here. They can release CH4 and CO2. And CO2, there's also the issue of the permafrost around the world may melt someday. The predictions are about 75 years, and then there's going to be a tremendous release of things that have been frozen for eons. And if that actually happens, there's a lot of trapped gases that'll come out, and that's not so good. And so we'd like to understand how this happens, and there's things going back hundreds of thousands of years from ice cores where you can understand how CO2 and ice are interacting. So these are just some of our very first results, and it's very rich. We're able to do kinetic energy implanting of CO2 into ice in ultra-high vacuum, so we don't need the high pressures of under the sea. We find spectra that we assign based on prior literature for amorphous CO2, clathrate, hydrate, crystalline solid background that we don't talk about, and crystalline solid from an optical mode. So we understand that CO2 can go in, and at these temperatures is mobile. They can cluster into little grains of CO2. And we can look at how they go in versus exposure time. We can look at all of these different optical transitions, and they all track nicely. And so we're able to now basically understand the embedding of CO2 into ice under a wide variety of conditions, and to see when it comes back out under a wide variety of conditions. In particular, we can do, don't laugh people, time-resolved infrared, meaning we can take a spectra every few seconds, nothing with femtoseconds, but we don't need that. And we can look at the embedding probability versus dose at different energies, and we can ask some very interesting chemical physics questions of what is the barrier heights for CO2 to become intercalated into ice. And so we can do that. And these are some of the first probabilities that we're seeing for embedding of CO2 into ice versus kinetic energy. And we have done some modeling that you can read about this summer, hopefully in a paper if it gets accepted. And you can see that we can look at the embedding probability for xenon, CF4, and CO2. And the CO2 looks kind of boring, right? You see all these green dots down here? It doesn't look like much is happening. But when you blow it up, it's really well above the error bars of our measurements. And so we can actually see the probability of CO2 going into ice, and we can do a model, a classical model, not yet a full MD kind of simulation. That's Bill Haas's now working on CO2 with ice, of course, my good friend. And we're now finding a suggested barrier height of order of half a volt. So we're understanding the energy you need for CO2 to enter ice under these conditions. And more theory on that to come. So I think I did it. 55 minutes, hope that's okay. So what I've told you about today are how we use visualization and scattering, much in the way you do with the APS, but in different ways, where one can look at dynamical processes on the nanoscale of visualization, on a small scale with STM. You can use scattering to do structure, and you can do scattering to do inelastic scattering with single phonon resolution. And so, while not a rival in many, many, many ways to the great APS, if you're interested in surface phenomena at interfaces, especially for well-defined problems, and for chemical problems, we do reactive scattering, which is not the topic of today. That could be another talk sometime if you ever have me back. Then you can learn an immense amount when you do this. I put up two pictures because there was a tremendous change in the group in 1 year, and I had to show you the people who did the work, right? You always have to show the people who did the work. This is a year ago, and Zach Hund and Kevin Nyhill and Ryan Brown were doing the methyl germanium, the methyl silicon work. For the polymer work, Hungju Ryu, who's now back in Korea, did the domain structures with time-resolved AFM. And Jonathan Rabin is a spectacular student who's doing now the time-resolved AFM studies with the video rate imaging. He's done a great job on that, and you'll hear about that. And Chen Tang was the magician. She's the one that did the single defect mobility in the polymer structures, which Other students, as I see Sonia sitting in the audience, an old postdoc, and there are several students who've tried to do, and they got their PhDs, but she nailed the problem. She took it to another level, and it's a pleasure to work with people like that. I put in this modern picture because the infrared team has now added Becca Thompson, who's doing great work, and Grant Langlois, who's actually the team leader now for looking at the infrared embedding chemistry of, he's the one who really wants to do the clathrates. So he's going to retool the machine over the summer, assuming we get permission from Washington to spend a little capital money and look at methane and agencies for funding. I also wanted to thank our many collaborators. And this is the last slide, for methyl silicon and methyl germanium, as I noted, we don't know how to make these things. They come from Nate Lewis's group at Caltech with his people, Keith and Noah. Giorgio Benedict is someone who I worked with maybe 25 years ago. We then saw each other, and now suddenly we're writing lots of papers together. It's great to have a long-term relationship like that. He's the best there is, actually, I think, in the world for calculating these phonon spectra. He worked with our group, Peter Tunney's group, Comster's group. He really owns that space. For the scattering work related to that, we're in Spain with Cristina Diaz and Fernando Martin, and they're doing a lot of the actual classical and now quantum mechanical scattering calculations for a lot of these systems. And the people who did the work for my group are in yellow here, I've talked about already. The ice embedding has a long line of people who are here, but at Texas Tech, again, a critical friend and colleague is Bill Haza, who does the MD simulations, so it's good to do that. For the polymer work, Miriam Friedman is now at Penn State as an assistant professor. Jim Becker is at First Solar. Ryan Brown is a postdoc at Notre Dame. Diana is professor at Loyola, and Hung-Shu Yuan is in Silicon Valley making hopefully lots of money to take care of us in our old age. And the scattering work in the polymers was complemented by the AFM, and I've already talked about Chen Tang, but Jonathan Rabin currently, Chin Zhang, Deepak, Seth Darling is here somewhere, I suspect, and Natalia Yufa, and for the infrared, the stimulated Raman Guillaume group made the nanorods. So with that, I'd like to thank you all for your attention. Okay.
John.
One thing I didn't quite get was in the case of the krypton and xenon saturating the ice, is it that there's only room for so much and when you put some in, something else has to come out when you put more in? Or is that when you put a certain amount in, it's stimulated desorption by putting more in? So are you filling it up, or when you get so much in, it's very easy to stimulate emission of more?
That's a good question. I will say with almost certainty, but it's a good question, that it's filling up the parking spaces, because most of the gases we've looked at are exhibiting that behavior. And the sputter yields are very low. I mean, I showed hopefully some very nice data on sputtering of ice, but the sputtering yields there are much lower than the embedding rate. So I don't think that's competitive. So I think it's reaching a place where the parking lot is full.
Can that be modeled theoretically with like molecular mechanics kinds of potentials and molecular dynamics?
Yes, it can. So I suspect you know Juan de Pablo now at Chicago, and so he really liked that we could pin the basic energetics for a few different polymer systems to verify his codes, if you will. And so the big MD simulations can do that. And so it's not all, the theory is well beyond mean field theories. What's interesting is all these defects have energetics to the surfaces of different domains, and when two things come together, there's less energy coming from the different surfaces, so the energy goes down a little bit. And a lot of that can be captured by simulation. So it really hangs together.
So I have a question. Over here.
Yes, hi.
The Debye-Waller factor, a lot of us know what that is for X-rays and when you have a single crystal moving around but when you talk about this Debye-Waller factor for these polymers, is it the whole polymer that's moving, or what are you measuring the motion of?
We're measuring the net displacement at the surface of the polymer chains. So if here's a big squiggly spaghetti, and it's breathing and moving, it's like an elephant. There's a little tail somewhere on the surface that's moving up and down, and that's sort of what we're seeing. Okay? So we're not seeing reptation, just to be clear, it's a good question, of the whole chain moving in and out. It's just the librational dynamics of the chains at the surface itself. Okay. And that can be modeled also by, very good molecular mechanics or MD simulations. Yeah.
For the case of the atoms embedded in ice, is it possible to observe Rydberg states? So in the solid state where electrons may be very far away from the nucleus?
I'm sorry, I couldn't quite.
So referring to Rydberg states in atoms,
yeah.
And where one might see them in gas phase, and I'm wondering, in the solid state where you've embedded the atoms in ice, is it possible to see Rydberg states in that state, in that situation?
Rydbergs, I don't know. I mean, I think that there are people in the audience who probably can. So if you want to do an optical excitation, but there is an electronic character to the embedding. These things are, clathrate-like. So, xenon in particular in ice, it's got some real chemical interaction. It's not just physically put into a pocket. I'm not sure if that's fully what you're saying. But, if you came in with an excitation of the atom to a high-leveling state, I don't know its lifetime in the ice, but so I'm not quite sure about that.
Okay. If there are no more questions, let's thank our speaker one more time.